All right, welcome everyone to our first CU Prime talk of the semester. So we have a lot of people here. This is wonderful. If you have never heard of CU Prime before, we're a great student org here on campus in the physics department, and we are designed to promote equity and inclusion within the physics community. And one of the ways that we do that is through this talk series. And so every other week we have talks from grad students featuring the work, their own research, and we get to hear it in a way that isn't filled with all the fanciful jargon that we usually hear in scientific work in colloquia. So today we are going to hear from Jacob Beckey, who's going to be telling us about some quantum entanglement things that are really cool. And if you have not gotten a chance to sign in on the laptops, if you're here in person, we do have a QR code. So go ahead and scan that with your phones really quick if you're able to. And that way you can sign in just from your phones. We don't have to worry about these wonderful Windows XP systems that are all broken. Right. Yes, so throughout the talk, feel free to ask any questions. The goal of this is that this would be a chance for anyone who's curious about these topics to be able to do so. And yeah, once everyone has scanned in that QR code who needs to, then we will go ahead and get started. So like I said, Jacob Beckey is a graduate student in his fourth year. He's working with Graham Smith over at Gilla, and he is going to tell you about quantum entanglement. All right, I'll let you take it away. Thanks.
Yeah, so thank you guys all for coming to the first CU Prime Talk. I'm excited to be here in person. Last year was on Zoom, and yeah, it's great to have everyone back in person. For the people joining on YouTube, I think there's about 300-400 people in person, so that is good. And today I'm going to talk about entanglement, which hands up if people have heard about entanglement before. Show of hands. Okay, sweet. So everyone has at least heard of, or most people have at least heard of entanglement. The CU Prime talk series, the main goal is to explain things from the ground up without a lot of jargon. Jargon-free might not be possible, but if you bear with me through a little bit of math, I think that at the end, it'll be rewarding to have some substantive understanding of what entanglement is. We're not just going to talk about what entanglement is, but also how it's useful. And that's really what the title of the talk means. Entanglement as a resource. You might have heard of entanglement as like spooky action at a distance or something, non-local correlations, these sort of buzzwords. But I want to give 3 examples of things you can point to and say, with entanglement, we can do better than any classical strategy or technology. And so that's sort of the overview. And then all CU Prime talks will end with a little bit about the speaker's sort of journey in physics and some advice just for anyone pursuing undergraduate research. So we'll start off with what is entanglement. Like I said, if you can bear with me through a little bit of background, then we'll get to the good stuff. We start off in quantum mechanics, a state. We usually represent it with this Greek symbol psi, and we put it in this thing we call a ket. And this is just a symbol for a vector. So the state of a system in quantum mechanics is described by this vector, and it's assumed that that is all there is to know about a quantum system. So as an example, can everyone see the slides, by the way? Good in the back, awesome. As an example, an electron has this property, which is kind of like an intrinsic angular momentum called spin, and it can be spin up or spin down. And we don't need to worry too much about what spin is, other than it's something that a quantum system has two possibilities. It can either be spin up or spin down. For the sake of this talk, we'll just take it on assumption that that's what spin is. Of course, not super fulfilling if you're wondering what spin really is. But for our purposes, we need to just take this as sort of an axiom and move forward from there. So one of the weird things about quantum systems is that the state of a system, which again, we're representing with this ket and the Greek symbol psi, can be in a superposition of 2 possible states. So it need not just be spin up or spin down, but it can be in some superposition of spin up and spin down. And this figure does not do a great job of representing this, but there's a bit of fuzziness to the arrow to try and indicate the idea that it's not in a definite state before you measure it. So before you measure a quantum system, you can have something that is kind of both spin up and spin down, a very strange state when you think of, compared to classical systems. And maybe you've heard about Schrodinger's cat. This is one of the famous analogies from the history of quantum mechanics that relates. The idea is basically a cat is in a box and there's some radioactive source that will decay with some probability. And if it decays, it will kill the cat. And if it doesn't, the cat will be alive. And so the state that would represent that before you open the box would be an equal superposition of alive and dead. And so that's what this is representing. And it sort of gets at the essence of like how weird superposition is. And that's what Schrodinger was trying to sort of illustrate with this example. And then the final piece we need. Question? So this notation was introduced by Paul Dirac. It's kind of just the standard in quantum theory. And I think, at least for our purposes, it's going to give us a nice way to just represent the state of a system as being spin up or spin down with just an arrow to remind you what the state of the system is. So I chose to use that as opposed to some, wave functions or something else that would be equivalent, just because I want a nice pictorial way to remember what the state of a given system is.
I know it's the standard, it's just curious why.
Yeah, so the reason that like these symbols specifically, like you're asking about the notational for itself, a lot of things you end up having to do in quantum mechanics involve taking inner products. So for people that have taken linear algebra, this is a special kind of product that results in just a number. And you flip this one and you call that a bra and you call this a cat, and together they make a bracket. And so that was sort of the origin of the notation. But for our purposes, it's just a notational choice to hopefully make things relatively easy to understand. The last piece we need is something called the tensor product. Again, that is jargon, but we don't need to worry about what the tensor product is, other than it's just going to allow us to summarize the state of one system and the state of another system simultaneously. So this little times symbol with the circle around it is a tensor product, and it just allows you to represent the system of two particles at once. Without being able to describe two particles at once, we can't really talk about entanglement. So we need this last piece. And then here, if you stuck with me, this is the background that we need sort of to talk about things in a meaningful way. So are there any questions before moving on? Is everything good? Sweet. All right. So I want to ask the first discussion question, and then I think the standard, Tyler, you can correct me if I'm wrong, 5 minutes of discussion-ish. So ideally, introduce yourself to your neighbor, get to know each other a little bit, and then discuss how does a spinning coin differ from a quantum system being in superposition. Okay, so that's me in the first discussion. 5:45, so we'll start back at a little bit before 5:50. If you guys want to discuss this question, how a spinning coin differs from a quantum system being in superposition. Maybe more like 4 minutes than 5 minutes. Very sorry. Does anyone want to share thoughts on this? Man.
All right, so and like a spinning coin, the only part that I understood that you meant was there is the same time. So everybody's still so there's a magic that's going on about.
Okay, cool. Thank you. So to repeat for people live stream, the idea stated was effectively you're constantly observing the coin flipping in the air. So maybe it's a little different than a superposition, which, like Schrodinger's cat, we're saying we haven't yet observed. Anyone else have?
Say that they have the same probability of what you're doing on the state.
Okay.
As examples, just up or down states. But kind of going up to be said, like during quantum state, you can't really observe it spinning per se, or during the fluctuating state. But when they observe that you can half the time do it in head, you're like half the state instead of even like without.
Yep. Oh,
So-
sorry. And then, yeah, either of you. Go ahead.
So I would say one of the differences you can sort of like imagine you could like sort of maybe describe the motion of the coin that spins. You could like come up with like a I don't know a simulation of how it you could, I guess consistently predict based off of how you like drew it where it lands, but with the quantum system, you wouldn't be able to observe it, so you wouldn't really be able to predict where it was looking to.
Yeah, and I think that's getting, maybe we'll stop there. That's getting really close to sort of, these are all good. Thank you guys for discussing and sharing your thoughts. I think this is towards what I had in mind. The idea that you're saying about coding up a simulation to do this, my thought was like, you have a robot, right? Boston Dynamics makes you a robot that perfectly flips coins, and you know every condition, or you evacuate all of the air in the room and you're able to just perfectly replicate it. Probably cheaper and easier to just code it like you said. But if you could do everything to control the system and flick it the exact same way every time, this would be completely deterministic. Depending on how you set the coin, like if it's heads and you know exactly how you're going to flip it, how many rotations it's going to give, this will be completely deterministic. You can think of it, if you know the exact friction force when you're flicking it on a table, this system, if you could completely know the system, there would be no indeterminism if it's governed by Newton's laws. Whereas in quantum systems, if you're in a superposition, even if you know the full state, meaning I know that psi state, even if I know that full description of the quantum system, the outcome of a given measurement is still indeterministic, still probabilistic. And so that idea is crucial to what we're going to talk about. So I just thank you guys for discussing and just wanted to bring that up before we get into entanglement, because superposition is crucial for understanding entanglement. So to illustrate the idea here, we have Schrodinger's cat at the bottom. I hope people back there can still see. You have Schrodinger's cat here in superposition. You open the box. That's the measurement. You're going to get either alive or dead. This is what we mean when we say we collapse the wave function. If you've ever heard this bit of jargon, it means that you're taking your superposition, you're observing it, and you're left in one of the two possible states. Okay. And this is completely probabilistic, even if you know the exact specification of your system. And that's what's so weird about it. Okay. So now that we have all this, we're able to really get into what entanglement is. We talked about superposition. And we talked about composite quantum systems. And it seems weird if you read this definition, it says something's entangled if it is not something else. And that seems weird because instead of just directly defining entanglement, we're saying this is what entanglement is not. So we're going to say something is entangled if it cannot be written as just the state of system one, tensor, when you say that tensor, the state of system two. Okay. So if you can't just write these things as in this way, then we're going to say it's entangled. So operationally, I want to, because this is probably new notation to a lot of people, I want to step back and see operationally what this means. And so we're going to assume that Alice, we're going to assume Alice is going to measure system one and Bob's going to measure system two. And pretend we have a bunch of copies of this state. So you have a bunch of exact copies of this state, and they're going to have, Alice is going to have system one in her lab, Bob is going to have system two in his lab. If they have 1,000 copies of the state, Alice is going to get spin up 1,000 times. Bob's going to get spin up or spin down 1,000 times. These measurement outcomes do not affect one another. And that's what we mean when we say things are separable. The measurement outcomes in one system do not affect the measurement outcomes of another system. So that's what it means to be able to write your state down as a tensor product. And again, the jargon tensor product, you should just think of, this is how I'm going to keep track of my composite systems. So I have 2 total spins. One is in Alice's lab, the other one's in Bob's lab. Okay. Does that make sense? Any questions? Okay. All right. So now we want to think about the following state. We want to think about it the same exact way as I just went through operationally thinking, all right, suppose I have 1,000 copies of this state. And this number out front, if you square it, it tells you the probability of getting this state. Okay. And so the 1 over square root of 2, I square that tells me that I have 1/2 probability of getting this state, where Alice will find spin up and Bob will find spin up. But I also have 1/2 probability of Alice finding spin down and Bob finding spin up. Okay. So we want to know, is this state entangled? That is, can we write it as just, a state analysis system and state on Bob's system? Again, it's always instructive to consider what happens when you do a bunch of measurements. So if you, again, give 1,000 copies, in mathematically, you'd have to take the 1,000 copies out to infinity to say exact things. But suppose they just have 1,000 copies that they have access to. and they tabulate what they find, Alice would find approximately 500 in the spin up state, and she'd find approximately 500 in the spin down state. And that's because you have this coefficient, and she has the possibility of being spin up or the possibility of being spin down. Bob, on the other hand, is going to find 1,000 spin up. Okay, so that means regardless of what Alice gets, Bob is getting spin up. And that's exactly what it means to be separable. So if you rewrite this, you can pull out Bob's state, and then you just have the state of Alice's system on the left and the state of Bob's system on the right. And that's exactly what we said is not entangled. Okay, this is a separable state. So again, a lot of new notation, but this operational interpretation is like, hopefully makes sense. The idea that this is, that their measurement outcomes are uncorrelated is what we mean when we say something is separable. Okay. Now, what about this state? Does anyone want to guess? Okay, we have a guess that it is entangled. And why would you say that? Yep. So he said, for people on Zoom, he said that he thinks this one's entangled because you can't separate it and just write it as Alice's system on the left-hand side of a tensor and Bob's system on the right-hand side. And again, I just want to encourage people to go through these sorts of things operationally. You get 1,000 copies. Now here's how things differ. Alice is going to find approximately half up and half down. But if they keep track of the order in which they get these different outcomes, Bob will find the exact same. So it's not just that they happen to get the same measurement outcomes, but every single iteration will exactly agree. So if Alice gets up on the first one, Bob's guaranteed to get up on the second one, okay? And so on for all the 1,000 iterations. And so if they meet up afterwards and compare, they would find that this is very strange, right? If it doesn't feel strange, I'm hoping the next sort of analogy will give some insight into just how strange it is, but to follow up on what was said in the back, if you, as hard as you try to separate this system out, you will not be able to write it. So I have the equal with a slash through it. You cannot write it as the state of system 1 times the state of system 2. Okay, so we say it is entangled. And to illustrate how weird that is, I have a very contrived analogy for you. I want you to think of 2 rocket ships, each with 1,000 coins. I picked the number 1,000 and I'm sticking with it for the whole thing. And imagine you have a grid so that you know which coin is which in each rocket ship. Okay, and you're going to set them spinning, and you can go as far in the distant universe as you want. You can be as far separate as you want. Alice in this one, Bob in that one. And you just want to be able to keep track of whether you get heads or tails when you stop them spinning, but pretend that we can keep them spinning for as long as we want. Okay. So the question is, if I measure, suppose I somehow, put a piece of glass over them and simultaneously stop them from spinning. Suppose I look at what I get. Alice gets heads, tails, heads. You start to compare with Bob, and he gets tails, heads, tails. And you start to look at all 1,000, and you see that they all disagree. So what is the probability? The question is, what is the probability that they would all disagree? If I have 1,000 fair coins here and 1,000 fair coins here, and I want to see what the probability of them all disagreeing is. So if you think about a single case, right? I have 2 coins. There's 2 ways for them to agree, heads, heads, and tails, tails. And there's 2 ways for them to disagree, heads, tails, and tails, heads, right? So what would be the probability of all of these disagreeing? Okay, very nice, very nice. Okay, we had the answer from the back. The probability of 1,000 pairs. So you're assuming they're independent coins. And so the first trial, like I said, 2 ways to get agreement. That's heads, heads, tails, tails. 2 ways to get disagreement. So the probability is a half. And then you have 999 more independent trials. So you have 1,000 independent total. And the probability of each is a half. So the probability of all of them is just the product of all of those. So 1/2 to the 1,000. So close to 0 that, we might as well just write 2. So that's what I want to, I hope that this somewhat illustrates how strange it would be if you were to get complete disagreement every single time you measured a state. And this was what bothered Einstein, Podolsky, and Rosen. They published this famous paper in 1935, introducing what they call the EPR, well, what is now called the EPR paradox. They introduced it. David Bohm, maybe people have heard of like Bohmian mechanics, a different interpretation of quantum mechanics, refined the argument, and I'm going to present his argument for it. And it'll sort of connect back to these points that we just talked about. So imagine beforehand you have some particle, some fundamental particle that in this case, we use the symbol pi and a 0 up top to indicate that it's a neutral pion. But all you need to know is it has spin 0. And again, we're not giving a satisfactory answer of what spin is, but just know that it has units of angular momentum. And just like in classical mechanics, angular momentum is conserved. And so in these fundamental interactions, angular momentum has to be conserved. And so we can just say that spin has to be conserved. So if I start with 0 net spin here, I have to have 0 net spin after. Okay, just conservation, just like linear momentum, energy, so on and so forth. So here then we have this decay that is able to happen. And maybe you've seen some decays on pictures from CERN. They collide particles and they look at how the things decay. This is just a very simple case of that, where the neutral pion is able to decay into an electron and what we call an anti-electron or a positron. So this is just an electron where the spin is opposite and the charge is opposite. Okay. You might wonder, how do we know that that exists? And if you've ever seen cloud chambers, there's this beautiful way to see particles sort of come into existence, and they leave a trail through this cloud chamber. And what you'll see if you do experiments of this, you'll see the electron curve one way and have some trajectory in this cloud chamber, and you'll see the positron go the other way and have the exact opposite trajectory. And the reason is, from the Lorentz, when you get into magnetism, you'll learn that the force that a charged particle feels in a magnetic field depends on the sign of the charge Q. Okay, so it'll curve one way if it's positive, it'll curve another way if it's negative. So anyway, hopefully I've at least given you a little bit of background on the fact that these exist. But for our purposes, all we need to know that this was spin 0 before, so afterwards the total spin has to sum to 0. What that tells us is that the state afterwards is going to be very similar to a state that we just saw, and it's kind of like an analog to how weird that classical coin analogy would be. This would reproduce 100% of the time complete disagreement. If you measure the first particle to be spin up, then you're going to have to measure, so if you measure the electron spin up, you're guaranteed to measure the positron spin down, because it has to conserve spin, and vice versa if you measure spin down and spin up. So if you had 1,000 copies of this, you would have complete disagreement 100% of the time. Whereas with coins, the probability of that happening is 1/2 to the 1,000, basically 0. So this is what bothered people and I suppose still bothers people, at least philosophically. But we've learned to work with it, and we've learned to harness entanglement as a natural resource, which is what the rest of the talk is about. But I hope I've given some sort of understanding so that we can all sort of have an idea in our heads when we're talking about entanglement. Now we know it's weird, but I want to convince you that it's useful. So the first one we're going to go through is something called non-local games. This will also be interactive, so I hope that the definition and winning conditions is clear, and then we're going to break up and we're going to try and beat this game. Okay, so we have Alice and Bob again. These are our typical, usual suspects in quantum info. And they're going to decide on a strategy for this game. I'll tell you what the game is here in a second, but they're not going to communicate after. So once the game starts, assume they're in different rooms, they're not able to communicate with each other, or they could be on opposite sides of the universe. Yep, Alice and Bob separate once the game starts. Charlie, the third party, is going to be a referee. He's going to have 2 coins. He's going to flip them, and whatever he gets, he's just going to send to Alice and send to Bob, and they're going to receive these coins. Okay, so 2 coins, assume fair coins, and they're going to send them up. And then Alice and Bob, based on their strategy that they agreed on, they're going to respond. Okay, and their response is either going to be heads or tails. Okay, it doesn't sound like that fun of a game, but again, if you bear with me, I think it's the conclusion is pretty cool, though it does seem like a contrived game. And now here's the winning conditions. So if they both receive tails, they will win if their responses disagree. Remember, they don't know what one another got. So they can't be like, did you get, we want to disagree, so I'll put heads and you put tails if you got tails, right? They can't communicate after. They don't know what coin they received. They just have to cook up a strategy such that they will win. If they receive tails, they'll win if they disagree. In any other scenario, so heads, tails, or heads, tails, they're going to win if their responses agree. Okay. So this is kind of a headache to even define. So I just want to give an example of an allowed strategy. I want to reiterate that they don't know what question they received from Charlie. And so let's just consider this strategy. So Alice, let's just say Alice and Bob are lazy, and Alice is just gonna say, I'm always gonna answer heads, and Bob's gonna answer tails, okay? So that means that they always disagree. So if you remember from the previous slide, so remember this strategy, they always disagree. From the previous slide, they win when they disagree only if they receive both tails. So how frequently will this strategy work? Sorry?
1 quarter, right?
Quarter?
1. So. Oh,
Yeah, no worries. So yes, because so the answer to reiterate is this will work roughly. You have to, this is in theory. If you actually did it in practice, you'd have statistical fluctuations. But if you do this over enough iterations, the probability you would find, they're going to receive they could receive any of these questions, right? Heads, tails, tails. The only time they're going to win with this strategy is if they both receive tails, which, because we're assuming they're fair coins, will happen about a quarter of the time. So yep, that's exactly right. All right, so knowing that, if you guys can go into groups, 25% of the time. Here are the winning conditions to remind you, and then just form small groups and try and find a better strategy for this game. Okay. And again, we'll give it like 5 minutes. Okay. Does anyone want to share their strategy for winning this game?
In honor of the time, the phrase "C sketch agrees." If you both agree to agree, you'll get 75%, and that passes.
Cool. So that definitely beats. So the idea is, we said, okay, if they both receive tails and they disagree, then they will win. But that only happens a quarter of the time. So the disagree strategy is not very good. And so it was pointed out that if you agree, then the other three three options will then be wins. And so you'll win if you average over enough trials, you'll win 75% of the time. So that's good. Does anyone think they can do better than 75%?
So basically, it would it goes so one of them so it is, I think it's positive fraction. So
Well, let's assume classical strategies. Maybe should have made that. You're one slide ahead, I'll say. So classical strategies that can beat 75%. Any?
And so in this case, we'll all be agreed for hat. Was 1 point five. If one of them gets tell, they're agrees to. So let's say Bob will give hat regardless of whether it's hat will tell, and Alice will always give hat will give tell only if Alice is also giving tell. So
I think with a whiteboard, this would be easier to go through. But what probability do you think you get with your scheme? You think you get 100%? Okay, so we can discuss after for sure. This strategy here with you might call it like a minimal strategy in the sense that you just do the thing that seems to make sense, is you just agree, because that covers 3/4 of the time. And you can prove that this is the best you can do classically. This is all the better you can get with classical strategies. And then, as Dement was sort of alluding to, if you're able to share EPR pairs, so like those states from the EPR paradox where you have complete disagreement, and if you're able to operate on your states as part of what they call a quantum strategy instead of a classical strategy, you're able to increase your odds to about 85%. So you're able to beat the classical method of 75%, and you can only get to about 85%. There are, however, 3-party variants. I'm sure this game was so fun that you would like to extend it so that another one of your friends could play. And if that is you, you're in luck, because there is a game with 3 parties. That game, classical strategy, is still 75% bounded, but you can win 100% of the time with quantum strategy. And so this is the first example where we can point to something and say, this is how entanglement helps. With entanglement, without entanglement, 75%, with entanglement, 85 or 100, depending on the game. And of course, the details are pretty messy, and in the hope of being jargon free, even though there's been a decent bit of jargon, we're not going to go through the solution, but if you're interested, we can definitely talk after. Okay, this is the first case. You might think this is incredibly contrived. Why do I care if I can beat this game? And what good is, beating the game anyway? If you've heard of Bell's inequalities, one of the things the CHS game relates to is Bell's inequalities, very important. But a couple sort of papers I just grabbed from Google Scholar. The one I wanted to point out is done with my advisor, Graham Smith, and others at Gilla. And playing games, they mean non-local games here. And multiple access channels, they're referring to a certain type of sort of quantum network where multiple people, there are multiple senders and one receiver. And you're able to use these games to sort of prove things about how much information can be transmitted through these systems. And there's these other papers that do the same sort of, they utilize these games to actually prove interesting things that have consequences for quantum technologies. So.
And you say that the gets
Yep, that's the top for 2 players, 85% is the bound. 3 players, you can reach 100%. That's called the GHZ game, if anyone is interested. Okay. So anyway, that's the first example. And I'm going to give you 2 more examples where you can point to, a system and say with entanglement, we can do better than classical systems. How many people have heard of LIGO? Okay, about half. So I'll explain in a little bit of detail what LIGO is. It stands for Laser Interferometric Gravitational Wave Observatory. Basically, if you've ever heard of the Michelson-Morley experiment, which was testing for the ether in the 1800s, it's the same idea, but on steroids. So it's this interferometer is 2 lasers. They interfere at a beam splitter, and then they go off at a right angle down, in this case, 4-kilometer arms. They race down at the speed of light, both of them. They come back, and if nothing has changed the length, the experimentalists set it up so that they'll exactly destructively interfere. So when one wave is at its peak, the other will be at its trough, and no power will get out, and they'll have a photodetector there to detect, and they'll get no photons out. If, however, something changes the length of these arms, then there will be some photons out. And from that signal of photons, you're able to read out something about the length of those arms. And of course, there are a lot of things that can change the length of the arms. For instance, like an 18-wheeler driving by, there's one in Washington and one in Louisiana. If you just get traffic nearby, they're so sensitive that they can literally shake the mirrors. Lots of noise sources, but once you account for the noise sources, the thing that they're really looking for are gravitational waves that come in and they squish one arm and they squeeze the other, they stretch one arm and they squeeze the other. And the gravitational waves emanate from objects like supermassive black holes colliding into each other and ripples going through space-time. And they literally change the length of these arms and then are able to be detected using these interferometers. So it's one of the coolest, technological feats of mankind, in my opinion. And you might say, where does entanglement come in? And that's a fair question. Like I said, you try to get rid of all the other classical noise sources, all the different technical noise in the electronics and stuff. And then what you're left with, and I apologize for the font, I'll explain what this plot is. The x-axis is frequency, the y-axis is sensitivity. And the red line, which is above the blue line you see here, is the typical sensitivity. So if you just account for, all of the noise sources that you can, you push it down, the noise as low as you can, you'll get this red line. So anything below the red line is too faint to be observed. And then with a special type of entangled light called squeeze light, you're actually able to lower that sensitivity curve down, and you're able to detect things that were that were previously not able to be detected. So something in between the blue and the red would now be able to be observed. And it looks like a small improvement, but this is something that will gradually get better over time. But it's another way to point to some quantum resource being used to surpass a classical technology. And so this is a very sort of high level overview of this. If you want to talk more about LIGO, definitely happy to discuss after. You might wonder, is entanglement necessary? You might say it does help. So you might say it's sufficient for an improvement, but is it necessary? In this paper in 2006, that has been cited probably a couple thousand times by now, shows that entanglement is necessary to outperform classical measurement techniques. You do need an entangled state to surpass what they call the standard quantum limit. That piece of jargon is confusing because it sounds like it's some quantum mechanical thing. But what that means is if you take into account all of the possible noise sources and you have the best possible performance for your classical system, they call that the standard quantum limit. And you can't surpass that without entanglement. And so this is the second way in which entanglement is a resource. Okay, any questions? Yeah, so squeeze light is a certain type of entangled light. The details, if you're interested, we can talk after. But yeah, to surpass sort of the sensitivity there are ways of lowering the noise floor of just like feedback from electronics and stuff. That's not necessarily a quantum mechanical effect. But the type of light that they're injecting into the interferometer is non-classical and it's actually entangled. And then they're able to use that to lower the noise floor. And yeah, happy to talk about that more. Okay, quantum computing. Final one, maybe people have heard of this. It's something that, has had a lot of press in the past couple of years. I'll give a little overview because we're sort of winding down on the technical part of the talk. Classical computers operate with bits, zeros or ones. Quantum computers operate using qubits, which, like we met, Schrodinger's cat can be in a superposition of 0 and 1. Okay, and so they need superposition, and moreover, they need entanglement to be anything other than really noisy, really bad classical computers. There's a way to make this like rigorous, but for our purposes, I just want to make the case that without entanglement, quantum bits, you would just write every state, you'd write 0, and then you'd have tensor 0 or 1, tensor 0 or 1, tensor 0 or 1 for however many qubits you have. And that would just be like having that many classical bits. There's nothing interesting there, and everything you do to it, if you can't use entanglement, you can't do anything that a classical computer can't do. And here's just some pictures of Google Sycamore chip. So this is Google quantum computer. This is like a nanoscale image of the processor, probably microscale. And they have about 50 qubits on this chip, if you've heard anything about Google's quantum computer. And the top one is a big dilution refrigerator. They have to cool it way down so the environment doesn't affect the processes. And all these leads in are to send pulses to control the qubits. And then the whole thing is cooled to extremely low temperatures to deal with noise. Okay, but the takeaway is without entanglement, quantum computers are just really bad classical computers. And now you might wonder, okay, but what are quantum computers good for? Does anyone want to shout out the prime factors of this number here? Thank you. It was very good. It was very fast. Next one. I will wait. 5 and 23. Wicked fast. You ready? You're up. Okay, so my point is, if we all got together and divvied up the labor, we still would not find these prime factors today or tomorrow or for a very, very, very long time. But that's just us with pen and paper. So you might, in this case, without pen and paper, you might wonder, can classical computers do that well? But it turns out that it's very hard for classical computers. And the best runtimes for algorithms, so you talk about a runtime, you talk about how long would I have to run my algorithm to solve the problem, is sort of the superficial way of saying it. And we say that the runtime is exponential in the size of the input. So, 21, the size of the input's 2, 115, size of the input's 3, and so on. So the size of the input is how big of a number I want to find the prime factors of. And to give you a feel for the difference between exponential and sort of a polynomial, you have, I'm only plotting from X. I realize that in the back, it might be a little bit hard to see, but I'm plotting X from, I think, 1 to about 15. E to the X, this is an exponential. X to the 5, this is a polynomial. And if I were to just zoom in at 10, I would see that X to the 5 is actually larger. So I might think that that's a worse runtime. But when you think about runtimes, you want to think about, as this problem scales to really, really large inputs, how are things going to work? And if I go out to even just 30, so now instead of plotting to 15, I'm plotting to 30. And suddenly X to the 5th looks flat. Okay. So that means if you could choose between having an exponential runtime or a polynomial runtime, you would choose the polynomial runtime, because that means for large numbers, I could still factor them relatively quickly. Whereas exponential starts to break down very, very, very quickly. Okay. So this is just a little background. Question? Yeah, so I mean, there's a bunch of different functions. I gave 2 examples here. I think in the next slide, you'll see why I gave these 2 examples. You have a bunch of different runtimes. The reason I mentioned exponential is because the best known classical algorithms have this scaling that looks like an exponential curve. And the reason I mentioned it is because encryption, so our banking, online shopping, everything that you want to keep secure, the standard method is based on the hardness of finding prime factors. So you use your key that secures your information is based on the hardness of this problem for classical computers. And so you might say, as long as it's a hard enough problem and a big enough input, then my information is secure. And that's what people thought for many decades. And then in 1994, a guy, a mathematician at MIT named Peter Shor, devised an algorithm to be run on a quantum computer that could factor large integers exponentially faster than any known classical algorithm. So instead of having the exponential runtime, you're going to have a polynomial runtime. Okay, so instead of it curving up super fast, you're going to have it still growing pretty slowly, even for large inputs. So this NIST down the road, I don't know if you guys know this, on Broadway, the National Institute of Standards and Technology is just down the road. They set all the standards for like a lot of weird things, like the standard size of, I think, peanut butter jars and just random stuff. They also define what the second is. They define cryptographic protocols, a lot of things that are just useful for a country and other countries to use as references. So this is just down the road in Boulder. The other satellite one is in DC, near DC, and their standard is using a 2048-bit encryption. So, we tried to factor a 3-digit and then, I don't know, maybe an 8-digit, and we were already unable. So then you're going to 2048, and you might ask, how long is it going to take a classical computer? Estimate is, about 100 trillion years, so longer than the age of the universe. So this is why they say things are truly secure if you use RSA 2048. But the reason governments got worried when Peter Shor published this paper is if you could construct, these are estimates, a 20 million qubit quantum computer, we're really far off. Remember, Google's state-of-the-art quantum computer is about 50 qubits. But if you could create a perfectly operating 20 million qubit quantum computer, you could break RSA 2048 in about 8 hours. So going from longer than the age of the universe to our scale is what scares governments, and is why there's a lot of funding going into both quantum computing and better cryptography to try and, guard against this. And this is like in the history of cryptography, this is always what happens. People have some protocol that seems secure, someone tries to break it, and then they have to come up with better codes, and then they have to try and break that. And if you've ever seen the Imitation Game about Enigma in World War II, you would be familiar with this sort of battle between cryptanalysts and cryptographers. Okay, this is your third example of how what you can point to and say, this is how entanglement helps. And for the last few minutes, I just want to take a step back from the sort of content, and part of CU Prime is about like fostering connections within the community at CU, and also providing some guidance for people that are interested in research. And so I just want to say a little bit about what theoretical physics students use on a daily basis. I mean, taking notes, using iPads, so especially during COVID, you can share with people. LaTeX is Overleaf over there, the logo. LaTeX, if you haven't heard about it, it's basically a very nice way to typeset equations, and all like technical papers in math and physics are written in LaTeX. And so if you're interested in going into grad school, it could be a really good idea to start using LaTeX, download Overleaf, get an account, and then when you turn in your problem sets, you could type them up in LaTeX. Some might call you a tryhard if you do that, but I think it's great. I'm looking at Ruben because he texts all of his notes constantly. It is actually a great thing to do. And then you're very ready for when you're going to publish your first paper, you're able to write it all up and you're fluent in that language. It's a lot like HTML and CSS. If people have ever used that, it's all about markup and telling the computer how to make things look. Mathematica, if you haven't met it, I'm sure you will at some point. Some people hate it. I see some eyes rolling. Some people, these all have their different applications, like Python. If you're doing something, you're doing some simulation of quantum systems, there's nice packages built in Python that make that way easier. Mathematica is really good at doing analytical derivations. So like, as an example, a quadratic equation, if you don't want to memorize the formula for the quadratic equation, Mathematica will just do it for you. And if you want to do the cubic equation, which is way harder, Mathematica will still do it for you. You want to take integrals that are hard, and you don't want to do by parts 3 times, Mathematica will do it for you. So if you haven't met Mathematica, as a student, it's good to learn the techniques that underlie it. But when you're actually doing research, you don't want to spend your time doing triple integration by parts, and you just want to find the answer. That's where Mathematica shines. Python, on the other hand, for my purposes, very good at simulating quantum systems. A little bit about my background. I studied physics and math in undergrad I did an REU. I'll give some information on the next slide about REUs and how to find them. Research experiences for undergraduates. Can't recommend them enough. Funded by the National Science Foundation. I think you end up, at least when I did it, the stipend was something like $5,000, $6,000 for 10 weeks of research. There's not like a lot of pressure in most of these. They're given to institutions that know how to foster sort of good research experiences for undergraduates. And so it's supposed to be a learning experience, but you still get paid. So definitely look into those. Really nice. Another one is science undergraduate laboratory internships. I did one at Oak Ridge and had a great time. They're less selective than REUs because there are just so many like national labs and so many advisors, and you can just reach out. I recommend emailing PIs, investigators, researchers at these institutions, especially for the SULI program, if you're interested in their research. And it can be a nice way to get a foot in the door. If not, if you've ever tried to email a professor, you might find that they're pretty bad at responding. A nice way to do it is find a postdoc, someone that has graduated with their PhD, but is working for this person, and try and reach out to them and say, I'm really interested in your research. You know, or is there funding for a summer student this year, right? And they're way more likely to respond. I then applied to fellowships and schools, graduate schools, got into CU. That's why I'm standing here. And then the other things that I recommend, which I'll talk about on the next page, are fellowships. If you want to take a gap year, there are a lot of fellowships that can fund you to get a one-year master's somewhere in Europe or in the UK, Canada. And then there are fellowships that fund your graduate research, and a great one in the same organization that funds REUs is funds a fellowship called the NSF GRFP, Graduate Research Fellowship Program, and they can fund your research. So you can have the freedom to sort of investigate what you're interested in. And you can apply to that once in undergrad and once as a graduate student. So it's a very good thing to keep on your radar. I know if you're in your first year, it might sound like a far way off, but it's nice to just have it on the radar and potentially, you know, you can tailor what you do and how you spend your time to prepare for these things. Again, maybe a little bit overwhelming, but for the internship search, this will be on YouTube. So if you can't get these right now, you can find them on there. Just for a general search, there's a site called Pathways to Science. Really good for searching for internships in all different fields. And NSF REU search. So this has to list, because it's a National Science Foundation, it has to list all of the different sites that they fund. And a lot of them, like CU's, I think has been happening since like the 80s. I'm not sure. Yeah, I'm not sure, but it's been like many decades that they've had REUs students here. DOE, the SULI program can be found here. And then the one fellowship I want to point people to is the Goldwater Fellowship. This is or maybe it's called a fellowship, but this is for undergraduates, usually upper level undergraduates that are interested in research, and this can fund your research. But more importantly, it then looks really good when you have that to then apply to other things. And the rest listed are various fellowships to fund postgraduate studies. You don't have to worry about it right now, but at least it's on your radar so that you can think about, you know, graduate school is funded regardless. Like a good program is going to pay you a stipend for doing research. You're not going to have to take out loans to go to graduate school, but these provide the opportunity to study in very cool places, UK, Europe, so on and so forth, or they provide the financial freedom to not have to work for someone, but rather have your own money and then be able to work with people. And so with that, I think I will conclude. Thank you for your attention. And
Great, thank you so much. We have time for maybe one or two questions for Jacob, if anyone has any.
Yeah.
you said you have?
Yeah.
Mhm.
And West was mentioned in both of the times. We were reference to a lot of.
Okay.
What exactly is the focus of
Like what he works on?
Yeah.
That's a good question.
This is Graham Smith.
This is Graham Smith. He's asking about what my advisor works on. So he works at Gilla. I can tell you that much. I know where his office is. No, I'm kidding. So what he works on is something called quantum Shannon theory. If you've heard of Claude Shannon, classical Shannon theory is having to do with how much you can compress classical information in a lossless fashion. So like if you compress too much, you're going to have errors in transmission, right? And he put like information theoretic bounds on how well you can do that. And then quantum Shannon theory is the same question, but imagine you're trying to communicate using quantum systems. So you have a qubit instead of a bit, and how far can you compress it in various communication settings? Trying to answer that and like the optimal rates of that is one of the main things he's interested in. But people in the group work on various things in quantum information. It's a very broad sort of field.
What like level of experience or education do you need from one of those undergraduate research?
Oh, that's a great question. Like for RUs, that's a great question. So I think the number one thing I hear from students that I've mentored that try to apply, the best way is to just, this is unfortunate, but it's true, is to find a way in through either talking to a graduate student or a postdoc and just like that, just have them take a chance on you regardless of your background. But if you just have to submit the application, I think a lot of them like seeing programming experience. So if you have Python or Mathematica under your belt, because a project that is feasible in a summer in 10 weeks with, you know, minimal background, maybe it's a new field. One thing that's definitely feasible is like a data analysis or a modeling project. Whereas with an experimental project, you know, 8 weeks in, you're still like aligning optics and it's just, it's way harder. So I'd say the number one thing that I've heard is programming experience, documenting that. Any outreach and research experience that you can get is great for those applications. Yeah. Hope that's somewhat helpful.
Another thing I think they prioritize in the studies is students who, students who come from small colleges who don't have many research.
This is true. Yeah. So the school I went to, yeah, very, very good point. The school I went to was an undergrad only institution. So they didn't have any graduate programs and they had basically no research. There were 3 physics professors and I graduated with 3 other physics students in my year. So I think that, you know, was a huge factor in why I got the RU. But RUs cater to underrepresented people in the field, whether that be race or socioeconomic status or anything else. So yeah, and that is one of the NSF's missions. Yep. Hope that is useful. Okay. Oh yeah, thank you guys again for your
If anybody has any other questions, are you happy to stick around for a bit longer?
I am here and
Great.
I am leaving some resources for people specifically interested in quantum information, which I felt a moral obligation to do so.
All right, well, let's thank Jacob one more time.